Hello everyone. Um, so today I will try to do some more problems on our YouTube channel, and today we'll speak more about forces. So the first problem I see here, it says that a light block of mass m and a heavy block of mass capital M are attached to the ends of a rope. Students hold the heavier block and lets the lighter block hangs below it as shown in the figure below. Then he drops it down. How much force in the rope tension while the blocks are falling neglect a resistance. So here in this problem I have a hand, the hand of a student. I have the large block and I have the small block. The large block has a mass of capital M and the small block has a mass of small m. So if the student is holding the large block, then there will be a tension force coming from the student's hand. But if the student leaves the block to fall, so what will happen is there will be no pulling force, there will be no tension force, and if we are also neglecting the air resistance, so the total force will be zero. So there will be no more pulling force acting upwards on the block small m. Of course, there will be a force of gravity which is pulling the two blocks down. However, we're talking about the tension force which is up. There will be no more pulling tension force. Okay, let's see the problem number 2, and it says that the radius of the Earth is about 6,370 kilometers, while that of Mars is about 3,440 kilometers. If an object weighs 200 newtons on Earth, what would it weigh on Mars if the mass of Mars is 0.11 that of Earth? Okay, so here we are comparing the weight of an object on Earth and on Mars. So as you guys know that we have learned that the acceleration due to gravity can be calculated using this equation. GE equal to capital G ME over RE squared. So that's on Earth. So what about on Mars? So I can just use the same equation. However, I need to replace the mass with the mass of Mars, and I need to replace the radius with also the radius of Mars. Then now I can divide these two equations, Mars over Earth. So the capital G will cancel out. Then I will end up with mass of Mars divided by mass of Earth multiplied by R Earth squared divided by R Mars squared. Okay, so I know that the mass of Mars is 0.11 that of Earth. So if I divide the mass of Mars by the mass of Earth, then I get 0.11. Now, what is the radius of Earth? It's 6,370. I put it here. And what is the radius of Mars? It's 3,440 kilometers. Now, of course, I don't have to convert kilometers to meters here, and the reason is if I multiply by 1,000 at the numerator and 1,000 at the denominator, then they will cancel out. So there is no need to multiply by 1,000 up and 1,000 down. So we'll end up with the gravity on Mars equal to 0.377 the gravity on Earth. But we don't need the gravity, we just need to know what is the weight of a 200 newtons object on Earth. So if I multiply these 200 newtons by the gravity on Mars, it gives me the weight on Mars, which would be 75.44 newtons. Now let's see the problem number 3. It says that a planet has a diameter of 10 times that of Earth and the mass of twice as large. If a robot weighs 1,800 newtons on the surface of the planet, what will it weigh at the surface of Earth? So again, I have Earth and I have another planet. So I can just simply use exactly the same equation that we have used in problem number 2. So it's a G planet over G Earth equals to M planet over M Earth multiplied by RE squared, which is R Earth squared, divided by RP squared, which the radius of the planet squared. Now it says that the planet um, it says that the planet has a diameter of 10 times that of the Earth. So what does that mean? It means that the planet is bigger 10 times. So if the diameter is 10 times bigger, then also the radius would be 10 times bigger. So I just need to put 10 here, which is the ratio between the planet and the Earth. And what about the mass? And it says that the mass is twice as large. So the mass of the planet is 2 times larger than the mass of the Earth. So now it's 2 times. So it's a 2 divided by 100, which is 1 over 50. So it means that the gravity of on the planet equals to 1 over 50 the gravity on Earth. So if the robot weighs 1800 on the planet, so what should it weight on Earth? So in this case, of course, this should be the weight equals to 50 times this number, so it should weigh 90,000 newtons on Earth. Okay, great. So now we can move on the next topic, the next a problem, and it says Khalid is pushing a box across a floor while Ahmed at the same time is hoping to stop the box by pushing in the opposite direction. There's a friction between the box and the floor. If the box is moving at a constant velocity, then the magnitude of Khalid pushing force should be what? Now, you should know that we have three forces, a force from Khalid and a force from Ahmed, which is opposite to Khalid, and also the force of friction. So I have Ahmed and the friction are moving in the opposite direction to Khalid. However, despite there is a force from Ahmed and a force from the friction, then this box is still moving at a constant velocity. So what does that mean? It means that the force of Khalid is greater than the force of Ahmed. And why is that? Because if the box is moving at a constant velocity, it means that the net force acting on the object equals to 0. And that means that Ahmed plus friction equals to Khalid's force. So it means that Khalid must be greater than Ahmed. Okay, let's now move on to the problem number 5, and it says that the figure below shows block A sitting on top of block B. A constant force is exerted on block B, causing the block B to accelerate to the right. Block A rides on block B without slipping. Which statement is true? So to describe this, we have two blocks B and A is sitting at the top of B. Now the block B is moving towards the right, but it's not only moving, it is accelerating towards the right, and we can tell that because there's a force that is pulling it towards the right. However, although B is accelerating towards the right, A does not move. So what does that mean? It means that there is friction force that is preventing the block A from moving. So if you imagine yourself in a car and this car suddenly moves forward and you're not putting a seat belt, so what will happen is you will go backwards, right? You will go to this side. So what is the direction of the force that should prevent you from sliding backward? This force must be towards the right because this box A, if there is not enough friction, it will slide towards the left. So which force will prevent it from sliding towards the left? It must be a force that is moving towards the right. That's why the block B exerts a friction force on the block A directed towards the right. Okay, so now let's look at the next problem, which is number 6. It says two objects attract each other with a gravitational force of magnitude 1 times 10 to the negative 8 Newton when separated by zero point 0.2 meters. If the mass of one object is 2 kilograms, what is the mass of the other object? So in this problem, I just need to use the gravitational force law that says F equals to capital G m1 m2 divided by the distance squared. So here I know the F equals to 10 to the negative 8 newtons, and G is a constant which is called the universal gravitational constant, equal to 6.67 times 10 to the negative 11 Newton meter squared per kilogram squared. Now, what is M1? M1 is the mass of the first object, which is 2 kilograms. What is the mass of the second object? This is unknown. And what is the distance between the two objects is zero point 0.2 squared. Then we can find the mass M2 by solving the equation, and it must be 2.99 kilogram, or it's almost about 3 kilograms. Next question, it says that the International Space Station orbits Earth at an altitude of h equal to RE divided by 16 as in the figure below, where RE is the radius of Earth. What is the weight of the 100 kilogram astronaut inside the station? Okay, so to know the weight of this astronaut, I need to know what will be the acceleration due to gravity at this height. So we know that the acceleration due to gravity can be calculated using this equation, G equal to capital G m over r squared. Now m is the mass of the Earth and r is the distance from the center of the Earth. So the mass of the Earth is me, and the distance from the center of the Earth should equal to the radius of the Earth plus the height to the International Space Station. So what is the radius of the Earth? It's RE. And what is the height to the International Space Station? It's RE divided by 16. Now if I do my math, then I have 17 over 16 RE all squared. Okay, now what I need to do is I need to know what is the weight at the International Space Station. So here, what I will do is I would say G International Space Station over G Earth equals to the um, radius of the Earth divided by the distance to the Earth divided by the distance to the International Space Station, which would be 16 over 17 in this case. So in this case, I will find that G International Space Station equals to this number, which is 0.885 G of Earth. Then I find that the gravity at the International Space Station equal to 0.8859 the gravity on Earth. And then I find the weight by multiplying 100 times the 100 is the mass times 9.8, which is the gravity on the Earth, times 0.885, and that gives me 868.1 newtons. Now the next question, number 8, says that the term force most accurately describes the quantity that changes the velocity of an object, because a force can do one of three things. It can either speeds you up or slows you down or change your direction. It's not energy, it's not inertia, it's not power, And of course, it's not the quantity that makes you move with a constant velocity, because the force must accelerate you. It cannot just keep you moving at a constant velocity. If you are moving at a constant velocity, that means that the net force acting on you equals to zero. Okay, the next question says that the figure below shows a 120 kilogram crate on a flat bed of a truck that is moving with an acceleration of 1.5 meter per second squared east. The crate does not slip with respect to the truck as the truck moves a distance s. What is the static friction between the crate and the truck? Okay, so first thing we need to find what is the static friction. Now, first thing, because this crate is not moving, then the static friction must equal to the force that is applied to the crate. Now, how can we find the force? The force equals to ma. That's based on the Newton's second law, F equals to ma. So m is 120 kilograms and a is 1.5 meter per second squared. So that gives me the force. And what should be the static friction? Should exactly equal to this force, so it's 180. But is it 180 no Newton east or 180 Newtons west? Now look at this. Now the car or the truck is moving towards the east. So what happens is if there's not enough friction, so what will happen is this box should be moving towards the west. So what kind of force will prevent it from moving towards the west is the force of friction, which must be directed towards the east. So one more time, the truck is moving towards the east and this box must be going backwards like this. So if you don't want it to move backwards, then you must apply a force, which is a static friction. So this static friction must be moving towards the east, towards this direction. Okay, now the next question says that two elephants, each of mass 2,000 kilogram, attract each other attract each other gravitationally with a force of 2 times 10 to the negative 5. How far apart are they if capital G, which is the universal gravitational constant, is this number 6.67 times 10 to the negative 11. So of course we will just use the same equation that says F equals to G m1 m2 over r squared. Now the force between the two elephants is 2 times 10 to the negative 5. The G is 6.67 times 10 to the negative 11. Now I have the mass of the first elephant, of the second elephant. Now I can find the distance squared, then take the square root. It gives you how far apart are they, which is 3.65 meters. And you guys may notice that although these are two big elephants with 2,000 kilogram each, that's a very big mass compared, of course, to our masses. But you can see the force between them is still very tiny. It's only 2 times 10 to the negative 5 newtons. And again, this is because of, you see, this constant is 10 to the negative 11, which really makes the forces very low. Okay, now move number 11, and it says that a car is rolling over a top of a hill at a constant speed v as shown in the figure below. If N is the pushing force of the ground on the car and W is the weight of the car, which the following is true regarding the magnitude of the two forces at this instant. So we want to know what about this force, which is the weight, and this force, which is the normal force. Now you must know, like, if the surface is flat, then these two forces must equal to each other. But because this cart is moving with a velocity v, then there must be an additional force which is keeping this cart moving in a circle, and this force is what we call the centripetal force, and it is also toward the center of the motion. So here toward the center of the motion I have the weight, I have also the centripetal force, which is keeping it moving in a circle. So this force must be bigger than the normal force. And again, the reason is because the car is moving in this kind of curve or part of a circle. Number two says that you hold the picture frame motionless against the wall by pressing on it by a force of 3.0 newtons as shown in the figure below. If the weight of the frame is 1.5 newtons, how much friction between the wall and the picture? So here you can see that this person is holding the frame against the wall, and we want to know, and the weight of this frame is 1.5 newtons, and we want to know how much friction is this. Now remember that friction is always opposite to the motion, and the thing is, if you remove your hand, what will happen is this block will move downwards because it will be affected by its own weight. So how to prevent this motion is by friction, right? And this friction will be upward, so it will be again 1.5 newtons. Now in problem number 13, it says that a 1.2 kilogram book lies on a table. The book is pressed down from above with a force of 15 newtons as shown in the figure below. What is the force acting on the book from the table below? So here we have a 1.2 kilogram book. So if it's a 1.2 kilogram book, so what is the weight of the book? It's 1.2 times 9.8. Now there is another force, which is the force from the hand, which is 15 newtons. So now I have two forces acting here on the table. One of them is 15 newton, the other one is the force from the weight of the block. So we need to know what is the force acting on the book from the table below. Now remember that is for every action there is the reaction equals in magnitude and opposite in direction. That's what does the Newton's third law say. So now I have two forces, 15 and this force. These are the forces downwards, so the disc will act with a force exactly equal in magnitude opposite in direction, which is 26.76 newtons. Okay, now let's see the problem number 14, and it says that a newly discovered planet has twice the mass and 3 times the radius of the Earth. What is the gravitational field strength at its surface in terms of the gravitational field strength at the surface of the Earth? Now this word called the gravitational field strength is just what we call the acceleration due to gravity. It's the same thing, right? So I will use the same equation I used, I think, in problem number 2, that G planet over G Earth equal to M planet over M Earth multiplied by R Earth over R planet all squared. Now it says here that the planet has twice the mass of the Earth. So M planet over M Earth equals to 2, but R Earth over R planet equals to 1 over 3 because this planet has 3 times the radius of the Earth. So the gravity on the planet equals to 2 over 9 the gravity on Earth, and we pick the answer A as the right answer. Now problem number 15, it says that if you press a book flat against the ceiling with your hand, in what direction is the friction force exerted by the ceiling on the book? So remember that you have to check the book and how it moves. If you remove the force, the book will fall like this. So it will no longer be in contact with any of these walls, as long as, of course, when it falls, it's away from this vertical side of the wall. So in this case, the friction will be 0. Of course, if we ignore air resistance, then the friction in this case will equal to 0. So the answer is A. And for 16 says that suppose one night the radius of the Earth doubled but its mass stayed the same, what would be the approximate new value of the free fall acceleration at the surface of the Earth? So we know how to calculate the acceleration equals to g, which is the universal gravitational constant, m divided by r squared. So if the mass stayed the same, but the radius doubles, so it would become 2r. Don't forget, it's a 2r all squared, which is 1 over 4 gm over r squared, or 1 over 4g. So it means that the gravity will be reduced by 1/4. It becomes 9.8 divided by 4, which is 2.45 meter per second squared. Number 17 says that the gravitational force of a star on an orbiting planet 1 is F1, planet 2, which is twice as massive as planet 1 and orbits at twice the distance from the star, experience gravitational force F2. What is the ratio F2 over F1? I guess the same idea, that we get the gravitational force gm over r squared, and what will happen if the mass is doubled for this other planet and the radius also is doubled? Again, it's a 2r all squared, so it becomes g2m over 4r squared. Now cancel 2 with 4, you end up with 2. So the g over this new planet equal to half the gravity of the Earth. So what would be the ratio between the forces? Again, it should be 1/2. Another problem about friction, it says that if you press a book flat against a vertical wall with your hand, in what direction is the friction force exerted by the wall on the book? So I guess this is just a repeat from another problem, which again, you see is if you press this way, but which way the block will fall if you remove your hand. If you remove this applied force, the block will fall like this. The friction must be upwards. 19 says that, ranking order from largest to smallest, the gravitational field strength on the surfaces of the following planets. Now, of course, I just need to use this equation, g equal to capital Gm over r squared. Then, for the first one, it would be m and r. For the second one, it becomes 2m and r. For the third one, it becomes m and 2r all squared. Remember, it's a 2r all squared. And for the last one, it becomes 2m over 2r all squared. You have to write these four equations and then compare them, and then you need to rank from largest to smallest. If you do that, you will find 2, 1, then 4, and then 3. Let's see number 20, and it says that on Earth, a scale shows that you weigh 585 newtons. What would be the scale read of your weight on another planet whose mass and size are less than their value on the Earth by 1/2? Now that means that the mass becomes m over 2 and the radius becomes r over 2. Remember, it's r over 2 all squared again, so it becomes g m over 2 divided by r squared over 4. So 4 will go upwards and 2 will go downwards, so it becomes 4 over 2. That's why I wrote 4 over 2 here. Now cancel 4 with 2, end up with 2gm over r squared, or 2g. So g is the gravity on Earth. So if it's double the gravity on Earth, then also the weight must be double. Then it's 2 times 585. That would be 1,170 newtons. Okay, so I will just stop here at this point. As you guys have seen, we solved several questions about forces here, and there are two things that you need to focus on: the friction forces and how you identify them in the picture, like for example number 18, and the forces that are coming because of the acceleration due to gravity and so on. Okay, so we'll just stop here, and I will see you inshallah soon in other videos.